will continue. Yeah.
Thanks a lot. Thanks a lot for inviting me. Yeah, happy to be here, although not in person. So, this is about SnakeMake and a new tool that we have published, at least as a software so far, not yet as a paper, recently, called Data Wizard, and how these two tools help to make data analysis more reproducible, transparent, and adaptable. So, data analysis, just to define it, I see as the process of going from some kind of raw data, some of observations, measurements, whatever, to some kind of results. And this is usually a heterogeneous process consisting of many transformations, filtrations, aggregations, the application of tools, algorithms, and scripts to create plots and tables and so on. And all of these plots and tables in the end are the results that you want to present when publishing or when communicating with your collaborators and so on. And of course, one can do that by hand, manually invoking stuff and so on, but this is can become a nightmare, especially if you don't document that very detailedly, and especially also when you scale this up towards hundreds or thousands of data sets. So therefore, people usually nowadays know that there are so-called workflow engines or workflow management tools around, and one of those is SnakeMake. So all of these tools have one common goal, and this is like has been seen as one of the holy grails in data analysis, and that is of course reproducibility. And people have called out the reproducibility crisis because there are so many publications that don't care about this at all and just publish their results without even sharing the code, or sharing code that is completely messy or spaghetti or whatever. So this is what workflow management systems, of course, primarily strive to overcome. But if you think about what reproducibility actually gives to you, this is quite a limited thing. So first of all, it allows to check the computational validity, the obtained results.
By the way, Johannes, we cannot see your full presentation now. Are you?
Oh.
Okay, yeah, could you?
It says here screen sharing was it was kind of interrupted. Let me try to...
Yeah, reshare, please.
Stop. And share again. Maybe the whole desktop, just to be sure.
Yes.
Okay, can you see this?
Much better.
Try to make it full screen. Okay, now this...
Cool.
Thing at the top is not gone. Better now?
Yes, perfect.
You see the slides changing?
Yes.
Okay, great. Okay, yeah, what I was saying is that reproducibility is a bit limited in thing, although everybody says this is like the holy grail. So we only can check whether something was computationally valid, like a result that was obtained, because like when we start the analysis again, we get probably the same plot or the same table or whatever. And we can, of course, also use this property to, let's say, apply the same analysis to new data and then get probably qualitatively the same results or some confirmation or whatever. This is, of course, a value by itself and very nice, but it's not all that is actually needed to ensure that the data analysis is of high quality, of sustained value for the scientific community, and so on. So therefore, I would argue that one needs to consider additional properties, and these additional properties are transparency and adaptability. So what does transparency mean? With that, I mean that actually somebody else who's not the author of the analysis is able to understand the analysis, what was actually done, what methods were chosen, and so on. Now, of course, one can try to explain that in a text, but ideally, it's not necessarily to write such a text, especially since such like textual method sections and so on never cover all the details that you could actually find in the code. So ideally, the data analysis code itself should be transparent, or you should be able to transparent this to make this code available to a reader in a transparent way. So what would that deliver? That delivers the ability to check whether an analysis is valid from a methodological point of view, and for somebody else to actually understand what was done. And this is, of course, important to judge over whether the choices are correct in the analysis, whether the conclusions drawn from it are valid and valuable for the reader, and so on. And the third aspect is adaptability. And that delivers the ability to modify the analysis later on, maybe even like 5 years later or 10 years later, ideally, if needed, and to extend it towards new research questions. And that is, of course, important for the author of the analysis himself or herself, because, yeah, it's not a one-shot thing then, but instead can be built upon later on for further scientific insights and publications. But it's also a value for readers of a paper because they probably don't need to reinvent the wheel when they want to do something similar, but probably can just build up on the work of others. And again, that is beneficial for the author because it would maybe generate more citations and so on. So these are the three main properties I think it is worth to strive for when conducting a data analysis instead of just doing it for the next paper. This is kind of the motivation behind SnakeMake as a system to make analyses that are not only reproducible but also transparent and adaptable, and allowed to do that in as little code as possible without as much boilerplate code as possible, and so on. And SnakeMake is around now since 2012, and since we count downloads in 2015, it has been downloaded a lot of times, like over 700K times, lots of citations, like on average last year, more than 10 new citations per week. So it's kind of one of the three big systems in the data science community, especially in bioinformatics, but also in other scientific fields, along with Galaxy and Nextflow probably, and probably also CWL. So what can we say about how SnakeMake makes it possible to achieve these three goals at the same time? So first of all, for being able to conduct a reproducible data analysis, it needs to be automated so that there's no manual step in between, because that always hampers the reproducibility. It needs to be scalable such that it works on the available resources and can be easily adapted to new systems, new clusters, new cloud environments, and so on. And it needs to be portable in the sense of that not only the code is important to conduct an analysis, but also the software environment it is working in has to be exactly the same as like during the initial analysis when obtaining initially the results. For transparency, there are other properties important. Obviously, it's important to actually understand the code such that it's readable. Maybe the code is not enough, so it needs to be properly documented, and you should be able to like trace from the results to the code, like which parts of the code were used to generate which results, which properties were used, which parameters, and so on. And all of these aspects in different form are also important for generating adaptability. So in the rest of the talk, I will show you how SnakeMake enables this by supporting these properties. So let's start with automation and readability. With that, I, of course, want to introduce the language itself. So the language that SnakeMake offers to write a workflow, so it's really something like a programming language, is based on one main paradigm, and that is that you decompose your workflow in single steps, and these steps are described by so-called rules. And these rules are written down in a text-based domain-specific language that is actually a syntactic extension of Python. So SnakeMake adds additional syntactical constructs to define such rules. And around these rules, like on top and below, and even inside, you can use pretty arbitrary Python code, which is what makes SnakeMake such a powerful system, because anything you can do in Python, you can also do in SnakeMake, but you have these rule constructs that make it very simple to design a workflow and connect steps with each other, and so on. So a rule always has a name. It has a set of input files, can be more than one. A set of output files, again, can be more than one. And something that describes how to obtain the output from the input, like a shell command, for example. And these input and output files can contain wildcards, as you see here. So these are placeholders in curly braces. And they stand for anything non-empty in between, basically, that can be inserted here. And this property SnakeMake can use to, for example, make such a rule generic. So in this case, for example, it can be applied to any sample that is followed by a .txt and contained in some data folder to generate some output that is in a result folder with, again, the same sample name and then, again, extension.txt. And you're completely free to choose these paths and so on. This variable part, of course, is then important for like rendering the shell command, where you have, again, similar placeholders, but in this case, these refer to the input files and the output files so that you don't have to rewrite those paths in there. And additionally to these simple constructs like input, output, and shell, you can define lots of other properties for the rule, like log files, parameters that are non-file parameters, like some thresholds or whatever, and resource usage, like number of threads the rule shall use or amount of memory you expect it to use, and so on and so forth. Then the idea of SnakeMake is that these rules are connected to each other automatically by SnakeMake matching file names against each other. So for every input file of a certain rule, SnakeMake will try to find other rules that can generate these, and by that it turns these rules into a directed acyclic graph of jobs that you see here on the right-hand side, where the edges denote dependencies between jobs and the nodes denote individual jobs. And obviously, independent parts of this graph can be executed in parallel, and SnakeMake makes use of this property of being able to compute this graph beforehand to schedule your workflow in the most efficient possible way. We will come to that later on. Okay. Then SnakeMake is not limited to shell commands for generating output from input. It has direct integration with scripting languages, and this is quite a unique feature as far as I know of SnakeMake. For example, it directly integrates with Python, R, Julia, and also Rust script, which is like Rust, but just in a scripting form where you don't need to write the full package management code of Rust and so on. It's just the Rust code by itself. For those of you who don't know, Rust is a compiled programming language that is very high performance with a similar performance as C, and some additional benefits of being very robust and checked at compile time statically so that your code is very reliable if you write it in Rust. And this boilerplate-free integration of scripts works as follows. So you just specify a path to a script, and then in the script you can directly access input files and output files of the rule, like you see here. And this is important because it makes scripting integration in SnakeMake very ad hoc. So you just write down the script and you directly access input and output and non-file parameters of the rules and so on. So what you usually gain by that is that you don't have to write like 20 lines of boilerplate code where you interpret input parameters, convert data types, and so on. You just can start immediately with the actual logic of the step. So making this as ad hoc is very encouraging at the same time to write very modular workflow code, which generates quite some readability and transparency in SnakeMake. So you won't be tempted to write like a giant script generating 20 plots for your paper, but instead you will generate your plots in many very small scripts. And very small scripts mean that they are quite readable and that the reader of a workflow can basically navigate via the rule syntax directly to the part of the workflow that is interesting for her or him, instead of needing to read your entire code base. So that generates a lot of transparency. There's also integration for Jupyter notebooks, which is like scripting integration, but it's interactive. In that case, you can specify a path to a notebook, and SnakeMake allows you to run that notebook in an interactive way, such that you actually can like edit the notebook in your browser until you're happy with the results that the notebook generates, and then you save it. SnakeMake integrates it into your workflow, and next time you can run it in batch mode, so non-interactive, and you will get the same, qualitatively the same results for the additional sample or other parameters and so on. And of course, you can re-edit the notebook in interactive mode at any time if you want later, like for iteratively improving the workflow and so on. Then SnakeMake has support for using wrappers to generate output from input. And these wrappers are meant to be used for tools that often reoccur in your field, like that you need to handle a lot. In bioinformatics, one example for that would be something like SAM tools or BWA, but also many other tools. And there is a database for these wrappers that you can use to take them from. And you see that this is like containing hundreds of wrappers that you can just immediately use by copy-pasting the example rules that are presented here into your workflow, and then immediately use them. So just as mentioning an example, for example, like when the SARS-CoV-2 crisis began in Germany, there were I'm working at a hospital, so we were asked to design a workflow for analyzing samples, whether they like which variant they contain and so on. And we basically composed this workflow just out of wrappers in 2 days, the basic version. Of course, then the development went on, but these wrappers make it very fast to quickly come up with something if you build on established tools in your field, in a sense. And they are more than just simple shell commands. Often they work around idiosyncrasies of tools, like with FastQC, there are some things in the way it saves files and so on. So the wrapper is really a small script that does lots of things, like renaming files and checking extensions and so on. So that can be very handy in order to not reinvent the wheel all the time and make certain tools that are kind of maybe weird to use more usable. Okay, then SnakeMake has lots of additional abilities to handle output files, for example. So you can mark output files as temporary, such that they are deleted when you don't need them anymore. You can white protect them if they are very expensive to generate and you don't want to accidentally delete them. Or you can even mark them as pipes, and in that case, the output will be streamed to the consuming job and never written entirely to disk, in case it's, for example, very big and you don't want to waste disk space for it, and so on. SnakeMake also allows you to combine additional workflows into your current one, and this works via the so-called module syntax. So you can define a module with a name that points to a snake file, so a workflow definition of an entire external workflow. You can pass on config to that module, and you can choose which rules you want to use from that module. For example, all of them, but also only individual rules of them. And upon importing such rules, you can even modify them, like modify their parameters, the input and output files, and so on. You can then extend such an external module with your own rules for your current workflow, and you can even decide to add another module, like for doing some kind of integrative analysis that, for example, I don't know, analyzes different data types, combines them into some integrated results or so, and the possibilities are almost endless there. Okay, next aspect I want to talk about is not anymore the language, but how SnakeMake scales to the underlying infrastructure. SnakeMake has a quite extensive scheduling algorithm that not only tries to maximize parallelism, but at the same time also tries to minimize the lifetime of temporary files such that they are deleted as soon as possible. This basically works by, let's say, once a temporary file is generated, scheduling the consuming jobs as soon as possible. And this works via this whole thing, like the whole scheduling problem, works via a mixed integer linear program, as you can see it here. And this problem here that we define here is basically solved whenever a new job becomes ready for execution in SnakeMake. Usually there's not just a single job, but multiple jobs that become ready for execution at one point in time. And this is like the superset, and we want to select a subset of these jobs for being executed next, given constraints that the user has defined upon execution. For example, the user could define to limit the amount of memory to be used, or the amount of CPU cores, or the amount of cluster nodes to be used, or cloud nodes, or whatever. Okay, so there are basically arbitrary possibilities there. Okay, and where the scheduling problem not only works the same way on local machines, but also on cluster systems and cloud systems, and it allows you to adapt the workflow execution according to your underlying infrastructure without modifying the definition of the workflow itself. There is another aspect that SnakeMake allows you to control, and that is especially important in cloud and cluster setting, and this is how jobs are submitted to the cluster or cloud middleware. So, for example, classical cluster middleware would be Slurm or PBS or Torque, On the cloud, it would be Kubernetes or Google Batch or Google Life Science API and things like that. So how does that work? So basically, you can instruct SnakeMake to partition this graph of jobs into bigger sets of nodes, and these sets of nodes are then called so-called groups, and each group is submitted together instead of submitting the jobs individually to the cluster or cloud middleware. That works by some command line argument called groups, where you basically take a name of a job or a rule and assign it to a group, and this name is given just, and the choice of this name is up to you. And by default, this works for each connected component. So if you define a group G1 for this blue and the green rule, each job from the blue rule that is connected to a job from the green rule is put into one common group. You see, we generate this way 5 groups here, which are submitted together. What is this behavior handy for? For example, if you imagine that the green job is very short running and the blue job is very long running, and your queuing time in your cluster system is like half an hour, you probably don't want to wait half an hour for a job that is just finished in 5 seconds or so. So by this grouping mechanism, you can attach every green job to every blue job that is like immediately before it. And by that, you just have the queuing time once instead of twice, and especially not for the short-running job. Okay, so this is kind of very handy in this case. Then you can also instruct SnakeMake to span with these groups multiple connected components by an additional argument, and of course you can scale this up towards like the entire deck, putting all of these rules at these levels into the same group, or splitting this up like here in the middle, and so on. So, and again, you don't need to modify the workflow for that. Instead, you can just do that, decide that during execution time. And by these mechanisms, like the scaling and the scheduling and the grouping, you can basically use SnakeMake to adapt your workflow to any architecture without modifying the workflow definition. There is one other aspect that I, in the interest of time, just want to briefly mention, and this is caching. So first of all, SnakeMake is by default lazy in execution. So whenever a result is already present on disk or remote storage or wherever you put your results on with SnakeMake, it won't re-execute that result, regenerate that result if it's already present. Unless some properties are fulfilled, like, I don't know, for example, one of the input files is newer than one of the output files, then such a job would be repeated and everything downstream. Or you force it to rerun certain aspects of your data analysis or so. And by that, by default, and for each and every workflow, it will, for example, happily handle things like adding additional data sets. By that, it will automatically see, okay, this part of the workflow I have to rerun, but that all old data sets that I've already processed, I don't need to process again. But there is one aspect that is not yet not covered by this, and this is so-called shared data. And especially in my field, like in bioinformatics, this is a huge thing. For example, we have these reference genomes and SNP databases and so on. You'll probably know that. And often they need to be post-processed, and this can take quite some time, like generating index files for them, sorting them, and so on and so forth. And meaning this is redundant computation if you really encode this into your workflow. And also it's kind of redundant storage in a sense, if you put this like in your working directory or whatever. On the other hand, not including this processing, downloading, and so on into your workflow means that you have reduced the reproducibility and need to document something that is kind of external of your actual analysis. So ideally, you want to include the handling of this shared data into your analysis, but you don't want to waste the resources for it, okay? So what SnakeMake supports to solve this problem is so-called between workflow caching. And this works as follows. For each job, SnakeMake can determine by looking at the code, the parameters, the software stack for the job, it can determine a hash value. And for downstream jobs, it can even include the hash values of the input files or the input code and parameters of the input jobs into the downstream hash value. And by those hash values, it can look up in a cache whether a certain result has been computed before. And such a cache can be, for example, group-wide or institute-wide or even machine-wide for different users. And by that, you can benefit of the results that others have already generated in case they are really exactly the same in terms of code, parameters, and software versions. This can be very handy for things like downloading stuff that is common from certain databases, that is like really properly defined in terms of releases used and so on and so forth. And that way your workflow can contain actually all these steps like downloading the shared data and so on without wasting resources on doing this over and over again. But instead you just take it from the cache, but you still have properly documented what actually was done to compute these results. Okay, next aspect I want to talk about is portability. So as mentioned, the code alone is actually not enough to describe data analysis. It's also important in which software environment it is executed. And for this, SnakeMax supports the ability to annotate rules with Conda environments. So as you probably know, Conda is like one of the widely used package managers, especially in science. And the main property of Conda is that it allows you to define isolated software environments in terms of simple text files, as you can see here. So basically you define a set of channels and you define the libraries and tools you want to use with particular versions. And these versions are, of course, important to really generate reproducibility. Otherwise, your software environment will change on each deployment, just taking the most recent version, but instead you want to fix them like this, okay? So what's nice about Conda is that this is very ad hoc, right? A simple text file included in the rule, and by that you generate two things. So first of all, the rule becomes portable. Will run on a new system that just has Conda and SnakeMax installed in exactly the same environment. And the second aspect is that the rule becomes even more transparent because it directly shows you what software was actually used in which version, and this is in a human readable way. So this is really understandable. Nobody can tell me that this is not like immediately understandable. I guess you will agree on that. So that is a very handy thing. The downside of Conda is that is quite a shallow environment. So it's not including the system libraries like libc and so on, and of course also not the kernel. Therefore, of course, there's an alternative, and this is container integration. In that case, you define like the URL to a Docker container or so, and then SnakeMax will use the container to run the shell command of the rule instead of running on the host system. The container is more secure in a sense of even pinning down to the system libraries. So the system libraries are exactly defined in the container, and if you run on two machines, they will use exactly the same system libraries and not only like in Conda case, the software that you define here. The downside of containers is that they are more cumbersome to create. You need to, like if you need a special new environment and not just some standard tool, you need to write something like a Docker file, upload it to some registry, be it your local registry or Docker Hub or whatever. And this is quite some overhead, also computationally. So what SnakeMax allows you is also like something like a sweet spot between the two, and this is so-called containerization mode. The idea of that is that you just write your workflow with Conda environments, so you write a Conda environment for each rule. Of course, several rules can also share the same Conda environment and point to the same one. And then upon like publishing the workflow or making it production, whatever, you can containerize it. So SnakeMax has a command for this, and this basically includes all the Conda environments of the workflow into one big Docker file. And when you build that and upload it somewhere, you can later on refer it in the workflow by using this containerized directive here. And if you then run SnakeMax with containers and Conda activated, it will actually take those Conda environments that are defined in the rules from the container instead of redeploying them. So that gives you the ad hoc development benefits of Conda and the transparency of Conda of being just able to read these YAML files here, together with the robustness, additional robustness of containers in terms of having like an environment that is really the entire system and not only some shallow software stack. That's kind of the idea. Okay, next thing I want to talk about is transparency and how SnakeMax supports that, apart from aiming to be particularly readable and modular, okay? And this, of course, is then meaning documentation and traceability. So how does SnakeMake supports this? Of course, you can just write comments in your SnakeMake code. Of course, you can also attach a README file to your SnakeMake code base explaining what you actually did there. This is all fine, and you can, of course, do that, but there is something more that SnakeMake offers you. And these are so-called self-contained HTML reports, also, as far as I know, a quite unique feature of SnakeMake. So for any SnakeMake workflow, you automatically can generate such a report as this one. And this report will, without further ado, always give you like the workflow graph, so the graph of jobs with the dependencies between the rules. It's interactive, so you can click on things here and you see like the software stack used, the input and output files, and even the code of each particular rule here, okay? And like this works for shell commands, but also for plots. Like in this case, we have like a script. If it would be a Jupyter notebook, we would see the notebook here and so on. So this documentation of the code, along with the semantic like dependencies between the jobs, is given to you automatically for every workflow that you write with SnakeMake without anything additional. And of course, you can probably imagine that this is even immediately for the people more handy than looking at just a GitHub repository, because you don't need to be an expert in like how you write SnakeMake rules and so on. You just see this visually and you can click on stuff and then you see like just the code you are probably interested in like a particular plot or so, okay? So that makes it more accessible for people. Then you get runtime statistics for free, like when were stuff created and how long did every step take and so on. And then, in addition, you can annotate any result that you define in your workflow, like any output file, to be included into such a report, okay? And in case you do that, you usually annotate this file then with like a description, a category, a subcategory if you need that optionally, and some additional labels, like you can provide something like text to these files, okay? And then all of these output files that you mark like this end up in this results category. And this results category, it can have subcategories as mentioned, but what you then see is like for every file, like the labels that you define. In this case, we have defined a topic label, which has different values here, and a type label. You see that the labels are displayed in the tabular way, like here. And then for each file, you can look at details about the file by clicking this I button here. And these details then include like the labels again, the description that you provided, and things like the file size and the rule that was used for that file. So from the result, you can even directly navigate to the code used to generate the result. And of course, you can also look at the result by this I button here. In that case, you see the result directly inside of the report, embedded, so to say. Okay? So yeah, these are the reports. And importantly, those reports don't need a server process. They are portable. You can email them around, put them on some file share, and so on. And they are working offline, so they don't need any online resources. So once they are generated, they will look exactly like this forever. And of course, like one possible application of this, and also quite often used application, is that you can attach this as a supplementary file to your paper, directly connecting, ideally, each plot that you show in your paper, each figure that you show in your paper with the code and the parameters, instead of needing to write this manually in a cumbersome way in your methods section. Of course, you can still do that, but this is at least an additional layer that generates additional transparency for the readers. Okay, then brief thing about this data wizard tool. So if you think about these reports that I've just shown, of course, you can include any kind of result in there, especially plots and things like that, but also in theory, Excel files and so on. Speaking of Excel files, this is of course a quite common thing in science. Many results are table-based, and often they are not based on a single table, but probably multiple tables that are related to each other, that have common columns, by which you, in theory, could jump from one to the next table and so on, like in a relational database in essence, but much, much smaller usually, okay? And often, of course, you can share this as an Excel file or a CSV or TSV file, but this is like not super readable and also not like interactive and so on. So what we thought like about 1 year ago now is that there must be a way to, let's say, come up with something more visual, something more interactive without writing like a web server that you need to maintain forever, that you cannot really port over, that you cannot put into a paper and so on. So the solution that we came up with is called Data Wizard. And in short, Data Wizard is like a low-code approach to interactively generate interactive result views for you from a set of tables, some relations between tables, and a set of rendering definitions for each and every column of these tables. Okay. So just very short, I don't have enough time to go into this into detail here, but just very short to give you an idea of Data Wizard. Basically, Data Wizard wants you to provide a description of your tabular data in YAML format, as you see here on the left-hand side. So in this case, we have two data sets, a data set in terms of a table that basically lists Oscar winners for the last years, and another data set that displays movies that are related to these Oscars, of course. This relation we can define via defining a link here between the one and the other data set. So for example, we have a link to the movie table that uses the column movie of the Oscar table to link to the column title in the movies table, okay? And vice versa, or the Oscar table here. And then we define, for each of these data sets, we can define one or more views, and these views basically describe things like how each column is defined, how each column is displayed in terms of, for example, having a link out in one column or having a certain plot in another column and so on. And on the slide before, I said that this is kind of a low-code approach, and with that I mean that we have lots of helpers in here in this YAML dialect that allow you to, for example, to render a column as a tick plot or as a heat map or whatever. And you don't need to write the plotting code for that, but instead you just define some YAML keys here and values, and the system will render it accordingly for you. And then Data Wizard uses some web technologies like Bootstrap, Vega Lite, and jQuery, and so on to generate an interactive data table for you. And an example for this, based on this Oscar and movie data set, is like what you see here. So here we have the rendering of the Oscars. This award column, for example, is rendered as a heat map. So depending on whether we have actress or actor, it's a different color, as you can see here. The names in the movies are rendered as link out. So if we would click here, we would, for example, jump to Wikipedia. This age is rendered as a tick plot, and so on and so forth. You can imagine that. Then we have a detail view, so certain columns are hidden by default, but if we click on this plus here, we see additional information like the birth date of the actor or actress and some kind of summary of their nominations and wins over time. And yeah, we can then jump, for example, to the movie plot for one of these Oscars. So these link outs are automatically rendered in the menu here. So if we jump here, we see the corresponding movie highlighted in the movie table, and so on and so forth. So you can easily imagine that this is not only useful for rendering Oscars and movies, but of course also for any other data science content, like, I don't know, biomedical results like variant calls, mutations, things like that, but also any other things in any other field. Okay. Well, with that, we are almost done. I just want to mention one more important resource about SnakeMake. So I mentioned before, SnakeMake is really widely cited and widely used, and there is the so-called SnakeMake workflow catalog, which automatically scrapes GitHub for SnakeMake workflows, and in case they follow certain standards, we can even present unified and standardized usage instructions like here automatically, so the authors don't have to write them. They just need to follow some standards, and then we can see always the same steps to run stuff like install SnakeMake, deploy the workflow, configure the workflow, run the workflow, and generate the report. And it's always the same. So if you know one workflow, you can basically use all of them. And in particular, you can also combine all of them as modules to generate some new insights by integrating the results of different workflows. Okay, so to conclude, SnakeMake is a system that aims to cover all aspects of fully reproducible, transparent, and adaptable data analysis. It does this by being particularly readable, integrating with HTML-based interactive reporting, being particularly scalable to any kind of computing or any kind of major computing architecture without modifying the workflow definition. And Data Wizard is a tool to, let's say, turn tables into something visually interactive without writing code, or let's say at least without writing lots of code. And that can be especially handy if you want to quickly visualize results for others without, let's say, maintaining a web server or something over time. And together, these tools are meant to make data analysis more reproducible and transparent. So as a reference, we have the SnakeMake homepage here and the GitHub repository of Data Wizard. Since this is still very new, there's not something like a shiny homepage yet for it. And most importantly, there is a new SnakeMake paper since last year, January, I think, which aims to be like an always up-to-date and complete reference. This is why we put this on F1000, so we can update this whenever SnakeMake receives a major new feature. This is also an invitation to you, so if you wanna let's say, engage with the SnakeMake community, which is very active and skilled, and lots of people are contributing to SnakeMake nowadays. If it's something major that really is worth mentioning in the paper, you will, of course, be at some point a co-author of this paper and up here. Okay, yeah, maybe just to name a few here, like Bryce and Michael, for example, have contributed Snake Format, which is a tool that automatically formats your SnakeMake workflows according to the best practices, which can be very handy. So you see that there's also tooling around SnakeMake to include improve your transparency and code quality. Felix Mölder, for example, has redesigned the scheduling mechanism. Vanessa has implemented Google Life Science support. Soyun has implemented Amazon cloud support, and so on and so forth. Sven and Alexander, for example, have implemented GA4GH test support, which is another execution backend. Manuel Holtgreve has implemented benchmarking support, and so on. So you see, this is really an active and diverse community with lots of people, and I would be happy to welcome you there. And may it just be as a user who reports a bug or whatever. So we are always happy to welcome new members in the community. With that, I would like to thank Alper again and all of you for listening, and I'm happy to take your questions. Thanks.
Thanks, Johannes. Thank you very much. It was a great talk, and I will have a couple of questions, but let's start here. Anybody wants to ask questions? Yes, please.
Thank you very much. That was an excellent talk, and we use SnakeMake in our work, and we appreciate it very much. I had a question. When you are using SnakeMake to submit against like an HPC execution environment, one of the tricks is to tune the resource ask correctly so that you have the right amount of memory and the right amount of time. So benchmarking becomes really important. Are there easy, simple ways to pull that utilization information out of the HPC and include that in a report that SnakeMake would generate?
I'm sorry, I couldn't hear all of it. It was not loud enough. Do you have a better microphone, or could you?
Or you want to come here?
I got it.
I'm really sorry.
Yeah, I could repeat, but.
Oh yeah, you can also repeat
But,
whatever you prefer.
You can come here. Come on.
Okay, so thank you.
That's better.
That's better. It's better. Okay, great talk, great tool. When you're using SnakeMake against an HPC environment, one of the tricks is to make sure that you're tuning the resource asks correctly. So you're asking for the right amount of CPU and the right amount of time and the right amount memory. So is there a simple, easy way to pull that information back from the HPC into a report that SnakeMake would generate so that you can look at that report and say, oh, I'm asking for too much CPU and I'm not using it all. So yeah. Yep. Thank you.
Very, very good point. Yeah, actually, you're right. This is the most, like one of the most important things when you design a workflow that you, if you run on HPC, that requires you to define this to come up with good estimates there. And so there is at the moment a pull request open where we want to enable by default to benchmark every single job. Okay, so like SnakeMake already has benchmarking support, so optionally you can activate this for a particular rule, and then it will benchmark the CPU usage of that job or every job from that rule and the memory usage and display this in a tabular format to you. So currently there's a pull request open that allows you to do this kind of benchmarking by default for every rule without specifically annotating each rule for that. And then you will get statistics exactly in the form that you actually need to estimate this properly. Okay, so then of course you could look at this data and define like runtimes, which is also part of this benchmark information, and memory in a more sharp way, even based on the input file size of the job and so on. So you can, in principle, even do machine learning for that. And speaking of machine learning, to do that, actually we have plans to try to infer this automatically. So given resource usage data and input file size and other information about the job, we would want to try to infer like an upper bound of resource usage. And what's nice, especially about workflows, is that you often have repeating steps that like are applied to lots of samples, for example. And then you can even you could even tell SnakeMake at some point to learn this automatically during the execution. So it could start with some rough estimates by you, but iteratively while running, it could refine this to something probably more accurate by looking at the actual measurements. So that will come at some point, but it's not yet there. So at the moment, really, yeah, you have to somehow guess. There's also a mechanism already now. This is called default resources, which by default gives you some rough estimates, so basically twice the input file size, assuming that the file is just read into memory entirely, and so on. So with that, you can come quite far in case you don't want to over-optimize this and just want to get it to run. But then you could, for particular rules, you could optimize it with your own prior knowledge and so on. But yeah, the default resources are a way to do this at the moment, but in the future, we will have this machine learning thing implemented at some point.
So thanks, Chris. It was a good question. Can I ask one more thing about the same thing, like for the optimization of the run? How do you want to like accumulate of all that run results or like memory usage, like the size of the set and everything? Where do you want to put it to run machine learning algorithms? Do you have any?
Yeah. So at the moment, in the pull request, but this might still change, the plan is to write it down in some message pack format such that it's stored in a binary way, so that it's not taking too much disk space. Of course, one needs to figure out like when you want to use this while still running the workflow, that you can access this as in a partial form, so if it's not entirely written for the entire workflow and things like that. Yeah, so but that still needs to be designed. So certainly it will go in the same direction as SnakeMake records its other metadata, so by being file-based instead of coming up with a server solution or so, because we want to keep it simple and accessible to everybody.
So one more. So do you have plans to integrate other ML algorithms or large language models, BARD, ChatGPT, or something like that, just to maybe write one of those like rules and start using it? Do you have anything? Do you have any plans? So in that field?
I'm still thinking about that. So actually, what I was testing already was like asking ChatGPT to write a SnakeMake workflow for me, and it worked relatively okay, so it can actually program SnakeMake, but it still made some mistake, like I don't know, not using idiomatic code here and there, and so on. So I tried to like iteratively refine that, and so on, and it worked okay, I would say. Also, GitHub Copilot is pretty good in writing SnakeMake code already now, so it usually gives the right suggestions, even better than ChatGPT so far. Like for example, like some months ago, I was giving a SnakeMake tutorial at the Dortmund University in Germany, and I actually had Copilot activated in my Visual Studio Code, and actually I wanted to like let's say do a live demo how you program, and like every single line was predicted by GitHub Copilot, so I had to deactivate it at some point. But of course, that's an easy task because it was like the usual tutorial example, which is all around the internet for SnakeMake. So, but even if you have something new, some entirely new workflow, it usually makes very good suggestions. So it is already somehow there, but I'm also thinking about further applications. So for example, ChatGPT has this new feature that was announced like, I don't know, 1 week or so ago on Twitter, of, let's say, being your data analyst helper or so. So basically you give it some task, like analyze whatever this data set for me, and it really gives you even plots and ideas how you visualize stuff and so on. So ideally, I would like it to not only give you those results, but also give you a SnakeMake workflow that basically generates these results. So I already wondered whether it would make sense to reach out to Microsoft or OpenAI about this, so that it's not only results relying on some particular ChatGPT version, but also like reproducible code along with these results. That would be really nice.
Yeah, perfect. Any other questions there? No? Okay, maybe I have one more question. So there are similar tools like Nextflow, other tools. So what in your opinion, what is the SnakeMake apart from other tools you are doing better than other tools? What you feel proud of?
Yeah, so I can make it, maybe I'm not the right person to really do this in an objective way, of course, but to some degree I know at least Nextflow, not so much many other workflow management systems, so I can maybe comment a bit of that. I would start with something SnakeMake is worse than Nextflow. So Nextflow is much faster in computing dependencies and starting up. So startup time in Nextflow is much faster. Sometimes with large workflows in SnakeMake, you need to wait like 60 seconds or so before it starts actually executing stuff. And in SnakeMake, this warm-up time basically is due to the fact that it pre-computes all the dependencies and makes its entire plan, although you can have also dynamic steps. But if you don't have dynamic steps, it basically pre-computes the entire workflow before starting to execute individual jobs. This is the downside of SnakeMake in a sense, because you have then this startup time where Nextflow just starts with like applying rules or steps to every single file on your disk that is in the working directory. The upside of this is that it has actually by that the ability to just print the plan for you, so a dry run mode. That can be very, very important in a cloud setting where you probably don't want to waste resources on a workflow that runs into completely the wrong direction or uses some unexpected parameters at some point or so. So you can really, with SnakeMake, you can give yourself a plan and check it before you actually run it. That is one big advantage, but at the same time also a disadvantage because it makes the system a bit slower than, for example, Nextflow. It has to check the existence of all the files before actually starting anything, which Nextflow doesn't need to do. The second advantage, in my view at least, is the integration with scripting and notebooks, because that is turning SnakeMake into not only a system that is meant for invoking high-performance command line tools, but also a very, very integrated way of combining, let's say, high-performance code with just scripting, plotting, and so on. And by combining this and making this, like also the plotting, modular and tightly integrated with the rest of the workflow, you gain a lot for the transparency, okay? And then this is like finalized by this reporting, which integrates the results with the code and so on. And that is, as far as I know, at least at the moment, in this extent and this deep integration, it's a unique feature of SnakeMake as well. So it's really giving you a solution from the raw data to the final plots of the paper, whereas other systems often aim at like making the part that is really needing high performance very easy and fast to compute, but they don't go the entire journey until the final results, in a sense. Of course, you can use them for them, but it's not as economic as it is with SnakeMake. At least that's my opinion. But of course, I'm super biased here, but probably somebody else would agree on that. I don't know.
Great. Any more questions there? No? Okay. Okay, thank you, Johannes. So after you, of course, I'll give the talk, but you already know, so if you want, you can stay or you can leave.
I will.
It's up to you. Okay. Thank you again.
Thanks.
Yeah. So let me share my screen. Okay. So first of all, working. Okay. So I'm a professor at UMass Medical School. At the same time, I am still running a bioinformatics core there at UMass Medical School. So we developed a software there, and like 100 labs at UMass started using, and we get some pool from the companies. They wanted to use our software in their own institutions or in their own companies, pharma companies. So we started a company to scale this up, because like running a bioinformatics core and supporting companies, both of them were pretty difficult for us, and we need to hire new people. We couldn't hire those people to the bioinformatics core. That's why we spin off a company. And UMass Medical School is our partner, so they are supporting us in every way. So this is my disclosure. And today, what I'm going to talk is, I'm going to start talking about our problem space, and then our background, how we spin off the company, and then I will talk about our product, like via Foundry. So this was called Dolphin Next before, so we had to rename it to spread the word out better, in a better way. And I will talk about our modalities and how you can start using in your own core in the future if you choose to, and where you can install. I'll talk about those, and I will give a little bit summary about the things that I talk, and then I will show a couple of more capabilities of our platform. So our problem was this. So data started accumulating in the labs at UMass, and we had to write a lot of code. And we were writing similar code to process the data for different type of analysis, like ChIP-seq, RNA-seq, or single-cell RNA-seq, or anything we do. We realized that we are repeating some part of the code, and we copy-paste and run to do the data processing. And then we realized that actually this is a waste of time. So we wanted to create a platform by creating some reusable modules that everybody can actually start using these reusable modules to create their own pipelines. And in the platform, we started with Nextflow to create the pipelines and execute them in Nextflow. And but today we are testing SnakeMake too, and in the future, hopefully, we're gonna be like language agnostic or pipeline manager agnostic. This is our plan. But because we see like lots of good things in SnakeMake, and we want to leverage our tool, that's why we started working on that. And also, as Johannes said, like there are good things in Nextflow. We just want to mix and match and use all the efforts in this area to help others. So I just want to talk about, like, this was a very hard job to start a company and getting the IP from the university and start working on that in the company together with the university, because there are lots of conflict of interest. So we had to solve all these things. If you are curious how we did, please send me an email. If you are planning doing similar things, I can help or I can tell you our story deeper. So we started with my PIs. So Melissa, I was working with Melissa Moore, and I was working with her in her lab. There were like 25 different scientists they were working on different technologies, experiments, and I learned a lot of different type of data analysis and processing techniques, and that helped me and us to create this platform, because we had to solve similar problems in different ways, and just this platform was born inside of there in her lab first. And then I started working with Manuel Garber, and he came to UMass from Broad Institute, and he brought all his knowledge. Maybe some of you guys already know Manuel. And he helped to shape up all this platform. And Melissa introduced me with Jim. And Jim was the like founder of Forge AI. So he came from AI perspective to the company, because we started using a lot of machine learning and AI algorithms now, and we are testing those things, because we process data, we collect metadata. Oops, sorry, I use my hands a lot. So we collect the data and we process data, and then later we start running some machine learning algorithms for profiling the data, like RNA-seq data or single cell, profiling the cell types, or optimization of the like used memory or CPU, those kind of things. We are trying to reduce the costs and also use all this information we collect for both science and also optimization purposes. So yeah, and Jim is helping us there. And in our platform, what we are doing is we are creating or is this good? No, I killed it. Huh? Okay. So, thank you. So in our platform, we try to create like holistic environment that the people can come, hopefully easily create and manage their pipelines. And in each pipeline, in SnakeMake that you have rules, and in Nextflow you have processes. We wanted to make it reusable, and also we wanted to abstract all this pipeline creation steps and attach it with metadata system too. Like you can, like if you start fully use all the functionalities we have, you can automatically process all your data from beginning to the end, from metadata collection. Imagine you have a project and you get all the metadata from a hospital. So they are using a third-party software, a database, like Benchlinks or Redcat. So we ingest data from those software into our system using APIs, and then running standard pipelines and accumulate the data back in metadata tracking system, some of them, if you choose to. But you can control everything in this interface. So what it is doing basically in the ecosystem, we have metadata tracking system, you have like pipeline managing system, but we are on top of SnakeMake or Nextflow or any other third-party pipeline manager. We don't have our own pipeline manager. We want to utilize their functionalities in our system. And we also have analytics section that you can create or define your own applications in the system by just defining the Docker container name and how you run that third-party software in it. Like it could be our Shiny application or some Python web application written in Python or Node.js or anything. You can basically define that application in a couple of steps, and then you can attach and visualize the run results in that application. It's very easy. We just started from beginning to the end trying to work on these areas. So for example, if you produce one R Markdown or a Jupyter Notebooks, you can easily launch Jupyter Notebooks or RStudio to start playing with the generated code, standard code. You can change it, save it, and share with the collaborators. So we are in that level. So basically we created lots of pipelines. Our users are creating lots of pipelines. And when they share with everyone, you can reuse those pipelines or modules. So this helped us to create lots of different pipelines, and also in any field. Like you can see, like, in epigenomics, we have a couple of pipelines. In proteomics, we have pipelines. Transcriptomics, everything. Like most of the pipelines in that field, because I'm working in RNA field. And we have other type of pipelines as well. And metadata, so the whole cycle is from beginning to the end. This is a cycle of data collection, running pipelines, and importing some other data, and running the some other third-party tools to manually curate some of the collected data in the metadata section, and then you can operationalize it after analysis or before analysis. So it means, like, when you add any data into metadata tracking system and add your files, it can automatically go from beginning to the end and give you some template files, and then you can go and do your downstream analysis using third-party tools, or you can create your own tools and add into the system. So we have these pipelines in these areas, and we are continuously working on adding like metabolomics and proteomics fields too. We have one integration with like proteomics, transcriptomics data with metabolomics. We are just now creating some scatter plots to show the correlations and those kind of things. But again, this is up to the people how they create their own visualization after data processing. So what you can do with our interface is you can do all the process management. So what we are doing basically, once you run all the pipelines, you can actually see all that reports, like how you run a process, how much memory you spend on that specific process. Those are coming back after running the pipeline. Like Chris asked that question, so can we get them back? So we also accumulate some data, that kind of data in the metadata tracking system that you can run machine learning algorithms for optimization purposes. But sometimes it's working, it's not perfect. We are trying. If you're running those on Amazon, it works perfectly because you decide about the machine type, like memory, CPU, and it's very reproducible there. But when I was running this on our own cluster, because the cluster is not like includes the same machine in every node, so this creates very like sometimes even you are doing exactly the same run. One of them finishes in 8 hours, the other is 4 hours. It's exactly the same run. That's why, like, machine learning didn't work well in our cluster, but on Amazon it works pretty good because it's very reproducible there. So these are the things that you can do to optimize the costs if you're running on the cloud. But on the cluster, so you have to be careful which queues you're choosing and how do you run your models. So, and also the organization management. So in the new tool in our platform, we added like organization management, that you can create a project, invite people into the project in different institutions, and create your metadata, share them in different levels, and then you can share the pipelines. The people can change the pipelines, add their own processes to process, so it can grow and change that pipeline or metadata part too. Then you can actually share this whole group. So once you get into the system, actually it simplifies code sharing or standardization of the pipelines, or standardization of the end results, data analytics parts too, because some people are working on visualization of, I don't know, GACA results, for example, and when others are focusing on other visualization or analytics, then you can put them all together into the centralized location, and this gives you the like institutional memory, or like in that everything stays in the project. Means like if we had this problem in our core, the people were coming, started working for us, like PhD students, postdocs, for 6 months, a year, and they were leaving. Before, when they leave, we were losing all the knowledge they added into the project, because sometimes they were running these things, these processes in their laptops, And then when they were leaving, they were giving you a code piece. And then when you try to run that code, it doesn't work anymore. So this platform is solving this problem. So everything you created here, you have to attach a Docker container or a Singularity. So then the code stays here too, that piece, and the person can reuse the other modules, and it can finish that task much faster than before, and also more reproducible way. So for example, I made a run like 4 years ago in our RNA-seq pipeline. It was revision 0, and today we are using revision 6. We added lots of other things into the pipeline, like Callisto modules, Salmon module, or lots of other aligners. And people are using different aligners sometimes to do the same RNA-seq analysis. And today I can go back and select the run, like duplicate the run, and I can rerun the same run I made 4 years ago with exactly the same parameters. Because Docker container is attached, you can run that forever. So this helped us a lot and increased our efficiency at least 10 times. And then sharing the data and sharing the pipeline also was a key thing. And also now, later we started doing the analytics in the platform too. We started supporting Kubernetes, and you can define a Docker container and then launch any third-party software to visualize the results. And we have our native applications that we created. For example, DE browser for count analysis. You can do differential expression analysis. And also other people created third-party applications like IC for single cell data visualization. We easily could put in those kind of applications. It takes like a couple hours. You just need to find that Docker container, and you need to learn how to run that in the container and a couple of lines, and then you can actually load the RDS object, for example, our object, into that file, and then visualize the results. We simplified all this process. You can add many third-party applications easily to your report section. So our dream, our plan is this. So we have the core and Foundry. We started accumulating lots of pipelines, and we started accumulating metadata of the projects. But then we started using like ChatGPT, for example. It's writing the code, as Johannes said, like it's not perfect. So we are not there yet. We are trying to create our own language models, large language models, by giving all the code pieces and training it with it. And we want it to write some visualization code or pipelines for us. It's working, but not perfect. But, and if we can achieve this, actually, we can speed up the pipeline creation steps as well. And also, we started integrating with the other models that you can actually integrate with Hugging Face models easily, and other models that you create to the system, because we are living in that area. Like you can create a block, and then that block can connect to any API to ask a question and get it back. So it's very easy that you can add a model into the system and work with any model. So our vision is accumulating these analytics or standard pipelines into our system. We also support NF Core pipelines too, and we are going to add SnakeMake pipelines into our system. Hopefully, we want to give this power to the scientists, that if they don't know how to code, they can still run all these pipelines themselves. But we want the bioinformaticians spend their time to add more value to their organization by adding new functionalities, new pipelines, new algorithms. So we don't want them to spend their time to recreate RNA-seq analysis pipeline again and again. So we want them to use what they are. So in our system, you can easily duplicate any of the process here, change it according to your need, and then save as a new revision and use for yourself and share with other people. So we have many modalities in our system that you can install this software into your core. We have like vCloud means our cloud. Some people don't want to manage a cloud on Amazon or Google. So they are using our service. Some of them are using their cloud, so they can install all this. This is just a web application, very lightweight web application. and you can run with a Docker container, and you can start it in your own cloud. And all responsibility, you're going to be the admin of that software, and it can run in your VPN. Some people choose running on their own cloud, and some of them runs their own on-prem servers. Like if we have a cluster in UMass, for example, we added one more node there just for this application, and it's using our cluster to submit the jobs for our users, and it's doing the authorization authentication with our LDAP server. It supports Okta server too. So you can do the authorization using user credentials. You can submit the jobs to the cluster and then get the results back, and they can manage their own environment themselves. But at the same time, they can define Amazon or Google Cloud. So sometimes our cluster is busy. You can easily switch, because everything is containerized. You can easily switch the run to cloud. When your cluster is busy, you can run it there, get the results back. So some people are using like that. I'm using like that. So what we want to do, we want to accelerate research. We don't want to reinvent the wheel again and again. We just want to share all these reusable modules with the people, make it open. Everybody can see the code behind it. If they like it, they can use it. If they don't like any part of that code piece, they can actually go and change and rerun that whole pipeline. So that's the transparency is important for us. Reusability is important, that when you attach any Docker container or Singularity, you can reuse the same pipeline and again. And also it shortens time of creating the pipeline, or also the management of all large projects. And also, you can always go back and see what you did before, and also you can recreate or reproduce all the results you run before. For example, I had a project, bear project, and they brought me like 12 samples, and these bears were in hibernation mode, and they collect the samples, they sequence and send me. And then I do the analysis, and a year later, they said that, hey, you have to do exactly the same run you did a year ago. Now we have 12 more samples from the same bear, and you have to do exactly the same run that we want to compare when they're hibernation versus non-hibernation mode. So, and this was small RNA-seq samples. It was like 4 or 5 years ago. And I got it, and I checked, because this was new at that time, this platform, and I checked. It was there. So I created all pipeline in the system. Basically, I duplicate the run, change the files, run. It took like a couple minutes just to run. So this creates like a lot of efficiency for bioinformaticians as well. Some people think that this is because web interface, bioinformaticians don't like using a web interface. They want terminal. You can run these things from the terminal too. We have like GitHub and Bitbucket integration. You can manage the pipeline here. You can create extremely complex pipelines by focusing on individual processes, and then you can push it to GitHub. You can add Travis or Jenkins, that it can be tested when you do any changes in the pipeline, and it's future-proof. So like you're not gonna get any bugs in the system, because it's always going to be tested after every push to GitHub or Bitbucket. And then the people can use seamlessly, like, without any errors, without any bugs. They can use, and they can always go back and use the previous versions too. And this will allow also knowledge accumulation as well in the metadata. This is connected to metadata. So you can trigger all these pipelines by just adding some files to the system. For example, think about like this. So you have a directory in your cluster or S3. In one bucket, if you add a new file, this automatically checks those files. If it's a new file in the same directory, it can trigger a pipeline and create all these standard reports for that pipeline, whatever you want to run. And then the user can go next day and start working on the process data. And you can run some of the data back to metadata tracking system as well. So this allows us to run some machine learning algorithms, because you're not always using the metadata when it's coming from the hospital or something. You have to also process, understand the quality of the data, and run some more processing, and you get more data back to the metadata system, and then machine learning algorithms starts running on that like daily basis to create some models for you. So this was our dream, especially for profiling data. Imagine you have RNA-seq data, and you don't know what it is exactly. What's the quality of the data? Imagine you run like enough RNA-seq samples to profile, like what's the quality of your samples, where it is when you compare to other published data. You can actually create a quality like value. We call this membership score, but imagine you think that your samples are liver samples, but when you profile it, you realize that like 40% of them are not liver. It's a contamination. But people are publishing their papers by believing that this was liver and finding some results without knowing exactly what's the percentage that they are coming from liver cells. So this is kind of like you have to do a lot of checks. This helps us to easily, fast, like profiling the data. I can talk till morning, but hopefully I will stop soon. So this, I'm gonna just talk a couple of functionalities we have. So you can ingest data using third-party apps with an APIs. You can define the API for data ingestion, and it's using a secure, like token-based technology. You can just enter the API of that software and also your token, and it will bring the data back in. And you can match the fields in the system without writing a single line of code. You can ingest the data in the tables or collections into the system. So we call them collections because MongoDB, we are using NoSQL, MongoDB database in the background in this part of the software, just to make the software more scalable. You can extend your project in time without corrupting your tables. That's why these JSON files help you to improve your metadata faster and easier. And we are also visualizing the project. The project manager can create the project by herself or himself. That like every project needs are different, but we have like some common needs to cover NIH like regulations that some fields has to be there if you want to push data to NCBI. We have them as a base, but every project can have different fields that you want to keep track. Like we had a skin project, for example. There are a bunch of things that we want to keep just because it's skin. Means we collect samples from the arm, or legs or someone else in the back. So there are many more information about skin diseases, but they are not in the system. So we needed to collect these systems in a hierarchical way because the person is coming. We collect this for like each patient visit. We collect some samples from different part of the body. And then for each, we call them biosamples. For each biosample, we derive some samples from them. For each sample, you can do different experiments on them, like ChIP-seq, ATAC-seq, and RNA-seq, for example, at the same time. So it has to be hierarchical. Usually other metadata trackers you just give an Excel sheet. It's much harder to track all these things unless you have this hierarchy. So we created this system. Without writing code, you can create this whole hierarchy. And then you define your own modules. It's like nested workflows. You can reuse the modules, and you can create, again, extremely complicated pipelines within the system. And this was the analytics part. You can create your own Shiny applications and launch it inside to visualize data. This is for single cell, for example, or anything you want. Like every day we are creating now a new Shiny app for different things. For GACA, we have one Shiny app. You add your own GMT files, for example, and then your fault changes, and then you start visualizing GACA results very fast. It took like 2 days just to create that small Shiny app. But there are many Shiny apps we started creating for visualization purposes because we have the file, fault changes, for example. You just want to visualize and share the results with your clients because maybe most of you are running a core and you have clients. So this helped us a lot to share the results with people inside or outside of the organization. And then you can share the results with the portal. So this is also API based. The people can go and log in to the system using bearer tokens, and then they can ingest the data to their RStudio, for example. Or this is a portal. You can access this portal and to see like what happened to your samples, like what kind of samples you have. You can create summaries without writing a code. You might have encode functionality, but you designed all the metadata behind it. It's very flexible, and we are improving and making much easier for our users. I think that's all. Maybe if you have questions, that I can take some. Thank you. I was the chair, so I cannot ask questions to myself. Yeah.
Who is the intended user for this sort of system? Like, so I mean, you talk about functionality, like including SnakeMake and Expo and things like that. So there's sorts of things that, bioinformaticians, you kind of need to understand how those things work in order to utilize them. But are you also making this usable such that people without any programming experience are able to build pipelines and things like that? Is that part of the goal?
So our goal is to increase the bioinformaticians' efficiency, our efficiency, and also give this functionality, like, because these modules are drag and drop. Scientists, without knowing too much bioinformatics or any language, they can create the pipelines according to their need and then run it. But we always check, or we tell people, hey, don't allow them to run anything by themselves. We also advise people how to run in the institution, but we are trying to help bioinformaticians to help their users faster and better, and then reuse their own pipelines or modules themselves faster. So this is the intention. The use case usually is especially startups. They don't want to hire a bioinformatician first, but they want to start doing these analysis standard pipelines, and they are asking, hey, can you please create this pipeline for us? Some cores are using that in Germany. One university is using this, and they created more pipelines than we have today. So they are giving this service to their users in the university, and they created lots of pipelines. Some of them they shared with us, some of them are private to them. But so you can reuse all these things that you created, all these processes you created, and reuse them and share with the users. If some scientists are so good, so they get training, and they don't know languages, but they know Bash, like they can run commands. For example, you're teaching that, for example, you guys are teaching how to run these commands. So if you know that, so you can add a couple of processes yourself to the system, but you can use existing processes that are like written Perl code or Python code in the system, but also you can add your own small processes to do like further operation without needing an admin, project admin. For example, in other tools, you cannot install any new software easily. You have to find a project admin in that software, and then they install it, and then you can use that specific portion of that process. But here, you are the responsible as a user. Some companies, for example, or some people, they don't want to allow other scientists to add new processes, but some of them give the full, like we do like that. We give full flexibility to the user. They can add like they can duplicate a whole pipeline, and then they can change the processes by themselves. Every process has a version here and revision, and every pipeline has a revision too. So this, you can create like many different type of pipelines using exactly the same pipeline, but easily switch. For example, okay, I was using revision 01 for this purpose, and then you can switch it and then use another pipeline, but it stays there. So in the runtime, we are creating next flow pipeline, or in the future, it's going to be SnakeMake pipeline in the runtime. And then when it's running, saving that whole pipeline there, and then you can always, and then also configuration files, and then you can always rerun exactly the same pipeline you ran before. So it's just helped us a lot to rerun the things much easier while improving the pipelines, while improving the projects, while improving the metadata. It just helped us a lot. Thank you very much.